Swayam Prabha. Digital India. Educated India.
System VMs in detail so that we can get some more idea about these stacks. So basically, the system VMs or system virtual machines are also called as hypervisors or virtual machine monitor or VMMs. So wherever you see this or encounter this term as VMM or hypervisor, that means it is the system virtual machine that is running underneath. Now, what is a hypervisor? Hypervisor is an operating system for operating system, because you can see that you have this hardware, and when you boot this entire system, the first thing gets booted up is this hypervisor, and then you have multiple OSs which will share the underlying hardware through this hypervisor, of course, but these virtual machines will have different OSs, let's say OS 1, 2, and 3. Now, this hypervisor will get booted up initially or in the beginning, and then OS 1 will get booted up, OS 2 will get booted up, OS 3 will get booted up. Okay. So hypervisor is essentially providing the virtual execution environment for entire OS and its application, which will be running on top of this operating system. Now, what was the advantage, or what was the difference between this hypervisor and the OS from the system, the computing system point of view? Because if you have had the operating system alone on the top of hardware, then the OS was supposed to get booted up in the beginning itself. And instead, now the hypervisor is getting booted up. And after that, your guest OSs will get booted up on these different virtual machines. Now, the key difference is that hypervisor here will try to get invisible or try to stay completely transparent. Because if you see the operating system point of view, operating system will, let's say, will try to access the hardware through several privileged instructions that we have seen before, like trying to access the file or trying to access the network or so on and so forth. So basically, you are initiating the privileged instructions from this OS for this hardware. Now, to get invisible, what this hypervisor will try to do is that it will trap those privileged instructions, and then it will emulate in the underlying hardware. Okay, for this underlying hardware, which is the underlying ISA. So guest operating system does not know at all that it is actually doing something else which it was not supposed to do. It was supposed to, let's say, try to access the memory or maybe disk or network interface. Then it will, or maybe let's say some IO devices it want to access, maybe some let's say your head microphone or camera it wants to try to access. Then it will initiate the privileged instructions, and the hypervisor will trap them and emulate them for the underlying. And that is the flexibility of using this hypervisor as the completely transparent system between this OS and hardware. So all the privileged instructions that are coming from different virtual machines, hypervisor can now schedule them for the underlying resources that are coming. So the hypervisor is completely doing the same thing as operating system was supposed to do, that scheduling, the resource management, the allocation. So everything hypervisor is now doing the same things, but for the virtual machines that is on top of that. So when guest OS gets executed, that privileged instructions, hypervisors intercepts the instructions and check for correctness, and then emulate that instruction for the underlying. And that is the difference between traditional OS and your hypervisor. Now, let's look about different types of hypervisors that are available. So there can be type 1 hypervisor, which is on bare metal or native. So basically, hypervisor is lying on top of your bare metal hardware, and then it is kind of uh, uh, trapping all the privileged instructions coming from the virtual machines. Let's say VM1 on VM2, we have two guest operating systems, and applications are running completely in separate environment, right? So VMware ESX, basically VMware has different hypervisors for different machines, like desktop, your server. So basically VMware ESX is server level system hypervisor. Zen also provides system level hypervisor, which is type 1 hypervisor. Uh, uh, so basically what these hypervisors are doing is that it tries to completely be transparent. So the virtual machines or the guest operating system which is running in the virtual machines, they will do they will initiate or invoke these privileged instructions to these hypervisors. Actually, they don't know that they are doing that to hypervisors, but hypervisor underlying that will trap them and emulate them and get back the result. So that means all the things, like basically when you're seeing that the stack, it is very important to understand that when you are booting up, your hypervisor gets booted up initially, so in the beginning, and then your guest operating systems will get. So that means to have or to control the hardware, underlying hardware, all the IO available inside this hardware, all the network or file system that are available inside the hardware, to have the control, you need the drivers also present inside the hypervisor. So writing hypervisor from scratch is kind of the type 1 hypervisor, because it is completely independent of everything, and it is underlying the all the guest operating system, and basically it is sitting on top of your hardware. So it must have all the drivers that will be necessary to access the hardware, underlying hardware. Now, type 2 hypervisor will give you some flexibility in terms of implementation. So what that does is that it is now no longer a part of your that means you are no longer writing the hypervisor from the scratch. Now, what you are doing there, you are now making the hypervisor a part of your operating system as well as part of your user space. So now the question is, why I will write all the drivers that are already present inside the operating system, right? Operating system has its own drivers and modules to control the underlying hardware. So why I will write all the things from the scratch, which is the type 1 hypervisor doing. So with the help of native operating system, so native operating system is essentially which is running on the bare metal hardware, and guest operating system which is running inside your virtual machine, which is not running in the on the top of your bare metal hardware. Now, on the bare metal hardware, your native operating system will be running. So why not taking the advantage of all the drivers and modules that are present inside the operating system and put your hypervisor in the kernel portion. So you write one kernel module inside the operating system to take over the privileges. That means to take over the control of all these modules, which will be inside your native operating system, and also provide some user level libraries or some links to run your user level applications, right? So now we have type 2 hypervisor, which is kind of hosted on the native operating system. So that is why it is also called the hosted virtual machine. Now, now you have this native operating system. So basically, all the native applications can be run on this native operating system. And if you have the virtual machine, that can be on top of your type 2 hypervisor, and all these privileged instructions coming from this guest operating system can be trapped and emulated inside this hypervisor. And that is the type 2 hypervisor we are of course, writing this type of hypervisor, we will not need much of effort because you are not writing from the scratch by implementing all the driver modules for controlling the underlying hardware. Right? There are another uh, sets of virtual machines called para-virtualized virtual machines, which modifies the so basically the virtual machine we have seen that modifying the gateways will give better performance for the para-virtualized virtual machines. Because if you see the traditional hypervisor with full virtualization, so basically they expose the virtual machines to virtual hardware through the which is for the underlying hardware. Now, of course, advantage is that you do not need to modify your guest OS. So guest OS can run as it is because it does not know that there is underlying hypervisor is running, because the hypervisor, which is the full virtualization type 1 by hypervisor, so that is completely running underneath and completely transparent. So basically, you do not need to modify your guest OS. Okay. But the disadvantage of this kind of hypervisors is that sensitive instructions must get trapped and emulated by the hypervisor. And all the sensitive instructions that are coming from your guest OS, trapping them and emulating them will cost these resources. So virtualizations like KVM, the kernel level virtualization, virtual machine, VMware SX that we have seen. So all these are providing you full virtualization, but of course they cannot add up to the entire or all the resources, take advantage of all the resources that is available because of this penalty of trapping and emulating, right? So para-virtualized VMs sees a virtual hardware abstraction that is similar to this, but not actually the real hardware. So basically what it is doing, guest OS is modified with replacing this uh, replacing some calls, sensitive instruction calls. So basically you have hardware, the hypervisor and the OS. So if the hypervisor wants to get fully transparent, then all the instructions, privileged instructions coming from your OS needs to get trapped into the hypervisor and gets emulated. Now you are saying that I do not want all the instructions to get emulated inside your hypervisor. Rather, you can have some of these sensitive instructions or define one set of the sensitive instructions, which will have executed through this hyper calls through hyper calls to your hypervisor. So now hypervisor is no longer transparent because now OS knows that this set of instructions or this set of sensitive instructions will be through hypercalls to your hypervisor, and this set of instructions will be normal system calls, right? So in that way, your hypervisor is now no longer fully transparent. Rather, it can capture some set of sensitive instructions through these hypercalls. So there will be now interface of this hyper call interface that we have seen that will come into picture now for these para-virtualized virtual machines. And providers like Zen provides both para-virtual and as well as full virtual machines for the users. Okay, and also this was another advantage because often these traditional hypervisor that we have seen are partially para-virtualized because the device drivers in guest OS may be para-virtualized to the hypervisor calls. Okay, so some mix and match you can do, and you can have this para-virtualized VM. So this is basically completely orthogonal to your type 1 and type 2 hypervisor that we have seen in the previous slide. Okay, so now next we'll talk about we'll see some of these hypervisors that are available. So these are the providers: VMware, Denali, Zen, IBM, Oracle, Power, VM, and you can see what kind of host ICs they can support and guest ICs they can support, host OS they can support, and guest OS they can support, and these are the companies by which these VMs are being provided. Okay, so now we have seen the two extremes of virtualization. So basically, you have traditional processes. So let's say you have hardware, host OS, and several processes are running on top of that. Now these processes are sharing the underlying resources, and complete multiplexing is happening inside these OS to share the resources between these processes. They may be taking one or several threads, and all these things will be actually controlled by the OS to have access to this privileged instruction for this hardware access underlying them. Now, what kind of isolation we have? Of course, the processes can see that all the resources that is available for me, but of course, some virtualization or multiplexing that is done by this OS in this level of multiplexing. You can see that several processes will be there, but they can see that the entire resources are for them, but the OS will handle which portion will go to him, and which resources will be allocated for which processes. If they are taking too much time, they will be preempted, and all these things will happen inside the OS. Now these are very loosely isolated. You can see that because let's say these processes will talk to OS through system calls, and there are, let's say, 400 near 400 system calls in Linux. Now you have all the system calls available for all the processes that is available on top of it, right? So that means they are very loosely isolated. So this is one extreme, and in the spectrum, another extreme is the traditional virtual machines that we have seen. So hypervisor will be there, and on top of that, we will have virtual machines, which will have, let's say, guest OS 1, guest OS 2, and on top of that guest OS, you will have several processes running. Now, these processes running on this guest OS will have no idea about what kind of resources or the isolation between the processes that are running on top of these two guest OS is completely rigid, because the resources that are being shared between these guest OS are completely managed by this hypervisor, right? So there is a complete isolation of how much disks or resources that will be accessed by this virtual machine and guest OS. So all these guest OS will see the hardware, and this process will only know that this whatever system calls that this process is invoking for this guest OS, no other system calls are there inside this guest OS for the from this process, right? Because these processes system calls will be routed through this guest OS, which is completely other virtual machine. So the isolation here is completely rigid, and this is kind of two extremes that we can see here, right? So system level virtual machines, we can see that each virtual machine has its own guest OS, own guest physical memory, which is virtualized view of the memory seen by this guest OS. And let's say one or more virtual CPUs based on the allocation by the hypervisor, and virtual IO devices, which is abstracted by the hypervisor to this virtual machine. Now, ideally, so you can see that these two guest OSs cannot see or share anything between them. Okay, so that is the main idea for this system level or system virtual machines. But of course, isolation of these processes are very important, because with the increasing workload for different application domains, what happens is that some processes we need isolated from completely from another set of applications. So limiting what we want to process, who will want to process, how much resources they can see, how much resources these processes can share. So all these are very, very necessary in terms of or from the point of view of isolation. So the processes that are sharing, of course, they can share too much because uh, their isolation is not high, and great isolation will be provided by the system level virtualization through these multiple isolated user spaces and sharing of one kernel and native performance. Okay. So what we will do is that we will go in between or the midway of these two extremes, which is the container based approach. So this is also one way of virtualizing things. But the thing is that here we are containerizing several processes which we think that these processes can talk to each other, but they need to be completely separate from, or there should be some isolation between these sets of processes and these sets of processes. And these are called containers. And this container concept was coined in the year of 2008 when Linux operating system started using the namespaces, because processes share namespaces. So if you contain the processes in terms of namespaces and control groups, then you can have isolated execution of one sets of processes from another sets of processes. So containers group traditional processes together and restrict what resources they can see and access. So basically, if you are familiarized with the namespaces, you can see that processes share namespaces. So if you create one separate namespace and control group for one set of process, then you can create one container and you can contain this process into these control groups and namespaces. So this concept is very, very important to understand the mid level of virtualization, where you cannot have the high or rigid, you can see still container is one process, because container will invoke system calls to this host OS, and then host OS to your hardware, right? And also this container will invoke the host process, system calls to this host OS, and so on and so forth. So in terms of virtual machines, so fully virtualized virtual machines or system level virtual machines, you cannot get that much of isolation. But since you have much more resources which are allocated for your full isolation of processes, you can have big resource gain in this approach of or container based approach, where you can have a kind of namespace separated between these processes and kind of uh, isolated execution or isolated resource share between these containers. Okay, so that brings us to cloud computing. So basically, we have uh, uh, talked about virtualization of at different levels. Now, if you virtualize everything, like your processing, if you want to virtualize, if you virtualize your storage, if you virtualize your software resources and as a service, that means you have seen all the software resources or the entire software stack. If you virtualize that also, okay, in terms of packing everything into one resource, and you share the resources. Now, as you share the resource of the entire software package as service, right? So now we have virtualized concept of processing, the storage, the software resources, everything as service. Okay. And these services now we can have, or the service providers, which who will provide these services, they can have a pay as you go service, because let's say how much distributed processing or how much processing you want, how much storage you want, what are the software resources you want to access. Based on that, you will be charged from the service providers. So that's all about the cloud. And according to the NIST's definition, cloud is a model for enabling convenient on-demand network access to a shared pool of configurable computing resources. Now, computing resources means, of course, the networks, servers, storage, applications, services, everything, right? That can be rapidly provisioned, so pay as you go, and released with minimal management effort, because as you are paying for the services, you don't want to manage or have more access to, you just want to just have access on all the management will be done by the service providers. So management effort, less or minimal management effort, or service provider interaction. So that is the formal definition of cloud, which is provided by NIST and widely accepted. And as the services that we are talking about, if the services are provided as, let's say, infrastructure service, basically customers can then provision the computing resources within the provider's infrastructure. So that will be called as infrastructure as service. You can have platform as service. Basically, if you or customers can want to create custom applications, so have some more flexibility in terms of creating applications, to have access to programming tools supported by the provider. So these will be called as platform as service, and software as service will be the provision where consumer uses provider's application running on provider's cloud. Okay, so this is the end user where you want to try to access the applications that are provided by the service providers. So basically, if you see from the different levels of uh, uh, of uh, of computing stack. So networking, storage, servers, virtualization layers is there, then operating system, middleware, then runtime, data, and application. So if you are operating on-premise, the entire stack of computing system. So basically, you have the entire server stack here, and that is managed on-premise. Then you have to manage everything. If you are taking infrastructure as service, then you have to manage only the from the software stack. So after the virtualization layer, so basically the OS, middleware, runtime, data, and application you have to manage, and the infrastructure basically, which is virtualized servers, storage, networking, everything will be managed by the company. So this was provided by Microsoft, and if you want to have platforms as service, only the application and data you want to manage, that you also you can have, and software as service, so all the applications only you will access, right? So just to have an idea how this cloud architecture works from infrastructure point of view, because there only there you have this the virtual machines which are actually working underneath, right? So you are the, let's say, user here, and you are talking to the cloud manager. The cloud manager will have a connection between these cluster managers, and cluster manager will have access to different sets of computing manager, which are essentially set of virtual machines, which will be running on top of one hypervisor underneath physical hardware that is present. So let's say one user is trying to access some resources in this virtual machine, and another user can access this virtual machine, but everybody will talk to your cloud manager through cluster manager, and cluster manager will be talking to your compute manager through high bandwidth network. Now, of course, all the metadata of these accesses, resource allocation, and everything will be managed inside your cloud manager to, let's say, several storage like data center object storage and so on and so forth. And the entire service will be managed as such. Okay, so as a user, you just want to access these machines, which are actually provisioned as virtual machines, which are managed by this computer manager. So who are the service providers? Just to have a look, like to have an idea what kind of service providers are there for different levels of services. So infrastructure services are provided by AWS, Amazon, Microsoft, Google Computing Engine. So these are mostly accessed by IT administrators. Software developers access the platform as service because you want to access the Google App Engine or AWS Elastic Beanstalk or maybe Heroku. So basically, from the applications point of view, users want to access Gmail, let's say CRM as service, or maybe Office 365, Google Docs. So all these will be provided as applications as service. So these are some examples of usage, but we have talked about the operating system, the computing system stack, the virtualization, different types of virtualizations available, and you can have actually virtualization in all levels of resources, and you can have the cloud, and different cloud providers will provide you different levels of access. As for the reading, this piece of PDF you can download from internet and you can read it. It will be very useful to understand what are the virtual machines that are available and how they operate. So broad level of the things that we have talked about here will be is actually written here very elaboratively by Smith and Nair. So this is very useful document if you want to keep it in your tool chest. So that's all about it. Thank you.